ARIS-10 is an open-source, low-cost 10.5 GHz phased array radar system featuring pulse linear frequency modulation. Available in two versions, 3 km and 20 km range, it is designed for researchers, drone developers, and serious SDR enthusiasts who want to explore and experiment with phased array radar technology. The ARIS-10 project aims to democratize radar technology by providing a fully open-source, modular, and hackable radar system. Whether you are a university researcher, a drone startup, or an advanced maker, ARIS-10 offers a platform to experiment with beamforming, pulse compression, Doppler processing, and target tracking. Key features include open-source hardware and software, complete schematics, PCB layouts, firmware, and software are available, dual version availability. ARIS-10N, Nexus, 3 km range with an 8x16 patch antenna array. ARIS-10E extended, 20 km range with a 32x16 dielectric filled slotted waveguide array. Full electronic beam steering, plus or minus 45 degrees electronic steering in elevation and azimuth. Advanced signal processing, and onboard FPGA handles pulse compression, Doppler FFT, MTI, and CFAR. A user-friendly Python GUI with map integration, GPS and EMU integration for real-time position and attitude correction, modular design with separate power management, frequency synthesis, and RF boards. The system architecture includes a power management board, a frequency synthesizer board that uses a jitter clock generator, a main board with DAC, mixers, phase shifters, front-end chips, and Xilinx FPGA for signal processing, and an STM32 microcontroller for power sequencing and peripheral control. The antenna arrays differ between the Nexus and extended variants, with the extended version using a GaN amplifier for higher output power. Processing stages are 1. Waveform generation by the DAC to create LFM chirps. 2. Frequency translation via mixers. 3. Beam steering controlled by phase shifters. 4. FPGA-based signal processing including IQ down conversion, decimation, filtering, pulse compression, Doppler FFT, MTI, and CFAR detection. 5. STM32-based system management for power sequencing, peripheral configuration, GPS EMU integration, and stepper motor control. 6. Real-time visualization through a Python GUI that plots targets on a map and provides radar control. Technical specifications for the two variants are frequency, 10.5 GHz for both max range, 3 km for the Nexus, 20 km for the extended, antenna, an 8x16 patch array for the Nexus, a 32x16 slotted waveguide array for the extended, beam steering, electronic plus or minus 45 degrees mechanical scan, 360 degrees via stepper motor, output power, approximately 1 watt across 16 elements for the Nexus, 10 watts across 16 for the extended using a GaN amplifier, processing, FPGA plus STM32 for both. Getting started instructions outline repository file placement, prerequisites such as a basic understanding of radar, PCB assembly experience, Python 3.8 or higher for the GUI, and FPGA development tools. Hardware assembly steps guide ordering PCBs, sourcing components, assembly using the provided schematics, selecting the appropriate antenna array, and enlisting the enclosure drawings. The project uses the CERN Open Hardware License version 2 permissive for hardware design files, allowing modification and commercial use under the same license. Software and firmware, including FPGA code, microcontroller firmware, and the Python GUI, are released under the MIT license for maximum flexibility. Complete documentation is available in the Docs folder and served via GitHub pages, with sections on system architecture, implementation logs, hardware bring-up guides, test reports, and release notes. Contributions are welcomed, especially from RF engineers, FPGA developers, software developers, and beta testers. Collaborations, licensing inquiries, or technical questions can be directed to the provided email address or opened as GitHub issues. The project currently has 19,000 stars on GitHub, reflecting strong community interest in open-source radar technology. The founder thanks all contributors for their support and encourages continued development of affordable sensing solutions.